Hello everyone, welcome to this lecture. So just a quick recap. In the last lecture we discussed about Cantor's diagonalization argument and we saw examples of uncomputable sets. The plan for this lecture is as follows. We will discuss about computable and uncomputable functions, and we will discuss about the existence of uncomputable functions. So what exactly are uncomputable functions? So they are some special type of functions. So say I have a function f defined from a set x to a set y, then I will call the function f to be computable if there exists some computer program in a programming language which can compute or give you the value of this function for every possible input from the domain of that function. Okay. So mind it, I am not focusing here on the running time of the computer program or the resources utilized for the program to give you the value or the output of that function. Okay, I am interested whether there exists a program or not which can give you the output of that function for every input from the domain. If you can write a program in the programming language for such a function, I will call that function to be a computable function. Otherwise, I will call it uncomputable function. Okay. So as per the above definition, a function which is not computable will be called an uncomputable function. Okay. So what we now want to prove is that there indeed exist uncomputable function. That means it doesn't matter how much resources, time, memory, space you provide and write down a program, there always exist some functions such that you cannot write down a program irrespective of the resources allowed to compute the output of that function for every possible input. And what will be the proof strategy that we will follow to prove this theorem? So we will begin with some known fact. So just recall that in one of our earlier lectures, we proved that the set of all valid programs in any programming language is countable, right? That means we can enumerate them even though there are infinitely many programs, valid programs. When I say programs, I mean to say the valid programs which compiles and give you an output. That means it has a begin instruction and an end instruction and a sequence of arbitrary number of instructions in between the begin and end instruction, and it compiles and it gives you an output. So the collection of such programs is denoted by the set P, calligraphic P. So in one of our earlier lectures, we proved that even though we can have infinitely many programs, we can always enumerate them, right? Namely, the cardinality of the set of all valid programs in a programming language is Aleph null. So this is a known fact. What we will prove is, we will prove that the set of all possible functions from the set of positive integers to the set of integers 0 to 9, call that set to be this calligraphic set F. We will prove that the cardinality of this collection of all possible functions is not Aleph null. Okay, that's what we are going to prove. That means what we are going to show is that we have more functions than the number of possible programs, because the number of possible programs is Aleph null, but we will show that you have more number of functions from the set of positive integers to the integers 0 to 9. Now, any program from your collection of valid programs can compute a single function from this collection F, right? You can't have the same program which gives you the value of both function f1 as well as function f2, because function f1 and function f2 will have different characteristics. How can it be possible that you have a common program p1 which simultaneously gives you the output of function f1 as well as it gives you the function outputs for f2? You can't have such special programs, right? That means if we prove this claim, then based on the known fact, we come to the conclusion that you have some function in this collection of all possible functions for which you can't find a matching program in the list of all valid programs in your programming language. That means there is no program in programming language which can help you to compute the output of that specific function, and that specific function will be an uncomputable function. Okay, so what is the proof strategy we are using here? We are actually arguing about we are giving here a non-constructive proof. Okay, just to recall, what is a non-constructive proof? Non-constructive proofs are used for proving existentially quantified statements. So this statement is an existentially quantified statement because it says that there exists at least one uncomputable function, and we are logically arguing that indeed one such function exists. We are not giving a concrete function for which you can never write a function. We are logically arguing the existence of such a function. So that's why this is a non-constructive proof here. So the set calligraphic F denotes, as I said, the set of all possible functions from the set of positive integers to the set 0 to 9. And my claim is that this set is not countable. That means its cardinality is not aleph null. Or in other words, you cannot enumerate out, list down all the functions in this collection. How we are going to prove this? Well, we already know a set which is not countable. What is this set? This is the set of all real numbers between 0 and 1, including 0. That's why you have the square bracket within 0, but excluding 1. Okay. So this set is already known to be uncountable. What we will show is, we will show an injective mapping from this set to the collection calligraphic F, which will prove that the cardinality of this set of all real numbers between 0 and 1 is strictly less than equal to the cardinality of the set of all possible functions. Okay, and since this collection is uncountable, any set which has more cardinality than that collection also will be uncountable. Okay, so how do we show the existence of the injective mapping? The mapping is very simple. You take any real number x between 0 and 1, possibly including 0. Okay, so it will have a decimal representation. Let the digits in the decimal representation be d1, d2, d3, dn, and so on. And again, I am assuming here that the number of digits in the decimal representation is infinite here. Why that? Because even if x has finite number of digits in its decimal representation, say for instance x is equal to 0.25, I can always interpret that 0.25 to be 0.25000. I can always plug in infinite number of zeros at the end. Okay, so that way I am assuming here that the number of digits in the decimal representation of every element x from the domain here is infinite. Now I have to tell you the corresponding image for this element x. The image is computed as follows, and remember the image will be a function because this set calligraphic F denotes the set of all possible functions from the set of positive integers to the set 0 to 9. So it will be, this set is basically a collection of functions. So I have to show you one function from this collection which will be the mapping of this element x. So what will be that function? The corresponding function f, which is the mapping of this element x, is as follows. The function f at input 1 will take the value d1. The function f at input 2 will take the value d2, and like that the function f at input n will take the value dn, and so on. So what basically I am doing here is that I am focusing on the function which gives you basically the nth digit in the decimal representation of your real number x, right? That's the function f here. Okay, and since I am assuming that I have infinite number of digits in the decimal representation of x, this function will take values at input 1, 2, n up to infinity. Okay, and the possible values or outputs of these functions can be only between 0 to 9, because each of these decimal digits in the decimal representation of x belongs to 0 to 9. Okay, so that's the function which will be the image for this element x, and it's very easy to verify that this mapping is an injective mapping, because if you take two elements x and y here which are different, then their corresponding or decimal representation also will be different. So x will be mapped to f and y will be mapped to a different function f dash. You can't have two different value and numbers x and y getting mapped to the same function f. So that's why clearly this function is an injective function. Okay, so we have shown here that indeed the set of all possible functions from the set of positive integers to the set 0 to 9 is an uncountable set. That means if I go back to the previous slide in the proof strategy, I have proved my claim. That means you have more number of functions than the number of programs which you can write in a programming language, and since each program can give you the output of only a single function from the set of all possible functions, you have more functions than the number of programs, and hence there are some functions for which you don't have a corresponding matching program, and that's why you do have uncomputable functions existing, right? So that's a very interesting theorem, because generally we believe that using computers we can compute anything. You can always write down programs which can give you the output of any function, and any task, any computational task in the real world, you can think it, you can abstract it out in terms of a function. So the remarkable thing about this theorem is that it tells you that computers are not kind of a god. It can't compute everything using computers or writing programs. There always exist tasks which you can't compute or can't find out their values. You can't solve those tasks using computers, irrespective of how much time or how much memory you are allowed while writing down the program. Okay, so and all these things we can prove. The theorem that we have proved, we proved using the theory that we have developed extensively regarding the cardinality theory. So till now you might be wondering where exactly the concepts that we have learned till now regarding the cardinality theory will be useful. So it is useful while proving the existence of uncomputable functions, which is a very fundamental fact in computer science. Okay, so that brings me to the end of this lecture. These are the references for today's lecture. Just to summarize, in this lecture we introduced the notion of computable and uncomputable functions, and we showed non-constructively that indeed there exist uncomputable functions which you can't compute by writing down computer programs. Thank you.